This video, we are going to look at from page number 11, I believe, and it's a dilution, a very dilute acid, and then common ion effect when you mixture of two weak acids. So we look at these types of problems, and the first one is a dilution, and we have 750 milliliters of nitric acid, and we have 15 molars. We want to, with a pH 1.30, and we're going to use stock grade 15 molar. So we're going to find out what is the volume that we need. So what if I have a pH of 1.30? What is that concentration? And we can just take the inverse log of negative 1.30, and it gives to be 0.05. So in other words, that's like saying you're preparing 750 milliliters of 0.050 molar of nitric acid from the 15 molar stock grade solution. So it's going to be quite a big dilution here. And look at, V1 M1 equals V2 M2. V said to M and M said to V, I'll meet you at the top of the chemistry. Chicka chicka boom boom. We get to use this problem right here. And we got the 750 and the 0.05. Those are the initial conditions. And then 15. Notice a big difference in concentration. So I expect this number is probably going to be a lot smaller than 750. And I look and do the calculation, it's only 2.5. So what I probably would do is pipette 2.5 milliliters of the 15 molar nitric acid, and then I'd add water. I don't know where this 47.5 came from. It'd be more like 647.5, but ultimately add enough water to get that to 750 milliliters and mix. Just a safety note, technically add acid to water. So you put a bunch of water in, add the acid, then you could top it off with the final amount of water. With such a small volume of acid being put in, I wouldn't be as big a concern if you were dumping a larger amount, but the rule of thumb is to always add acid so you don't spatter that. Okay, what about a very dilute acid problem, or would also work for a base? Well, let's say I have some nitric acid. I say, it's a strong acid, so the H plus is 1 times 10 to the negative 12. I say, well, that corresponds to what? pH of, that would correspond to like a pH of 12. Or that would say, my OH minus is 1 times 10 to the negative second. Be careful. This is really, 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 really dilute. There's also water, and that is a concentration of H plus 1 times 10 to the negative 7. So the water will dominate here. The acid will contribute nothing to the pH, but it will remain neutral. You're not going to combine an acid to neutral and get a base. The water will actually dominate because it's such a trace amount, and it just remains as a neutral pH. Last question, what if I combine two weak acids? And I'll look at the Kas. It depends on the concentrations in the Kas, but these concentrations are the same. And this Ka is clearly 10 to the negative 5th, clearly larger than the 10 to the negative 10th. So because of that large order of magnitude difference, all the H plus is going to actually come from the one that, even though it's a weak acid, it's stronger weak acid than the other one. So the stronger weak acid, essentially, unless the Ks are really, really close, is going to be contributing all the H plus. So how do we do a problem like that? I look at the acetic acid. Remember, I say it doesn't break down very much. It loses X, 0.50 minus X is about 0.50, and I can solve for X, which is H plus, and it ultimately ends up being what? The square root of Ka times the concentration of the acid, just like you do another weak acid problem. I plug in my numbers, I get 3 times 10 to the negative 3rd, and I take the negative log of that, and I get 2.52. So we're assuming all the H plus that's donated is going to come from here. This H plus is going to be, that you'd get from this would be very small. But now it asks to find the Cn minus concentration. So notice this almost becomes like, or it does become like a common ion effect problem, because we have the H plus from the breakdown of the weak acid, and then this H plus is going to skew the equilibrium back this way, lowering the amount of Cn minus than if you were just doing just taking the square root of Ka times this right here. So I put a 0.50 there, I put the 0.0030 here, that's a 0. It's going to move this way, but it'll be insignificant, x will be insignificant compared to the 0.50 or 0.0030. So I'm just going to plug things in here, and I'm solving for Cn minus. I know everything else, and I end up plugging in and getting 1.0 times 10 to the negative 7th molar Cn. Notice if I would have taken the square root times this concentration, it'd probably be somewhere like 10 to the negative 5th. But because this H plus drives equilibrium, that Cn minus concentration becomes less in this case. So if you have two weak acids, and assuming there's any type of discrepancy in the Kas at all, the one with the higher Ka is that's really going to contribute all the H pluses. The one with the lower one won't have a significant contribution to that. All right, that's page 11. Hope that helps.